Hi and welcome back, folks. So in the last lectures I covered countable and uncountable spaces, which I understand is actually a difficult topic to wrap your head around, but mathematics is like that. If you don't get it at first, then you try again. You look at the parts which you don't understand and try to understand those with much more better focus. So it's an iterative process. I never guaranteed that you will get it in one fell swoop. And practice problems. So take a textbook, just practice problems. You will reinforce your knowledge that way. Okay, so now the topic I'll cover in this video is conditional probability, which is all about these sort of questions. If an event X happened, then what are the chances that another event Y will happen? So in much better terms, how does the occurrence of one event M influence the occurrence of another event A? And the central number that we are concerned with in that is the probability of A given M. That's what this notation is all about. A bar M is the probability of occurrence of A given M has occurred. And if probability of M is not 0, then the probability of A given M is the probability of A intersection M divided by the probability of M. Weird definition, I know, but let's look at this from a frequentist approach. So the probability of A given M according to this definition over here is NAM over N upon NM over N. So this is the probability of A intersection M and the probability of M. Okay, so cancelling these out, you get the number of trials where A and M occur together divided by the number of trials where only M occurs. So notice this is like transforming the whole probability space into something where the sample space is only the events where M has occurred, and you're trying to find the intersection, that is the overlap of the event A with this sample space, that is the outcomes where the event M occurred. And that's pretty much what it is. It's kind of like, reducing your search space. So if someone just says that, okay, give me the probability of A, and they don't give you any prior information, so you have to search the whole sample space, which is quite big. This omega is quite big, and you have to search the whole sample space before triangulating which outcomes trigger the occurrence of the event A. And then you'll say, okay, the probability of A is this based on what sort of measure you choose for measuring this event A. Okay, but what about this? If someone told you that, okay, give me the probability of A, but M has already occurred, and so you would narrow down your search space to the outcomes where M has already occurred, and from there you will find the events where A will occur as well. You will find the outcomes which trigger the event A, right? And this overlap region is what A intersection M is. And the probability in the frequentist approach is that's what it's all about. The trials in which A and M occur together over the number of trials in which only M occurs. So you're basically reducing your sample space to something where only M occurs. Okay, I hope this explains what this sort of definition is all about, and this is something that I'll give you as a homework. Omega f p of something given M, now that's a probability space in and of itself for any event M. So what I'm trying to say is this probability of some event that you'll substitute from F given M, this probability measure follows the three axioms that we have defined. So try proving it for yourself. And from conditional probability, another nice concept that emerges is the concept of total probability. So this is kind of like a game where you have, let's say, multiple routes to go through, and your end goal is, winning a prize. Let's call that B. So if I take this route, or any of the routes, what are the probability that I'll win the prize B? So this is win B and this is lose, and similarly for the other route as well, there will be something else, right? This is what the concept of total probability is all about. So putting it in formal terms, suppose we want to calculate the probability of event B, which is what the magenta event in this diagram is. and your sample space omega is partitioned into these chunks a1, a2, an, all these things, and all of these partitions are obviously mutually exclusive. That is, ai intersection aj is phi for any I not equal to j. And now see what I'm doing. This is actually a pretty nice and neat trick. So split b into different chunks such that each chunk belongs to exactly only one partition. So this chunk I've highlighted right now is the chunk of b that belongs to only a2. This one is the chunk that belongs to only a3. Right. So you can basically write b as a union of all these chunks, and that is written as union of b intersection ai. So each chunk, that is this thing I have highlighted, is what? B intersection a2. It's basically the common elements that belong to b and a2. That's what this overlapping chunk is all about. And now each of the chunk that b has been split into by themselves are also mutually exclusive. So, and this is inherited from the fact that each partition is mutually exclusive. So that's why any other chunk of b will be mutually exclusive to all the other chunks as well. And now we can use the axiom of countable additivity to write our probability like this. So that is the summation of probability of b intersection ai. And this b intersection ai can be written in an interesting way if we just observe that the conditional probability b given ai is the probability of b intersection ai divided by the probability of ai. So using this over here and just moving the denominator to the LHS, we'll get this. Each b intersection ai term can be split into this. Okay, and we are anyways taking a summation, so this will apply for all ais. And so this is the total probability theorem. And to explain what this is about, I'll draw this probability tree. So as I said, suppose this is a game and you can take paths a1, a2, a3, an, any of those, and in each of those paths there's a probability that you will win the prize, that is b. So the probability that you win the prize b if you take, well, path a1 is p of b given a1, and similarly if you take a2, that will be p of b given a2, and so on. And now the probability that I take the path a1, a2 is given by p of a1, p of a2, all these things, and that's what I'm doing. I'm adding the individual probabilities of winning the prizes. If I go through this, if I go through this, if I go through this, right? If I go through each of the individual paths, what is the probability that I'll win the prize given that I'm going through a1? So the probability of going through a1 and winning the prize is p of a1 times p of b given a1, and then through a2, p of a2 times p of b given a2. So do that for all the paths and add that up. That will basically be the probability of winning the prize, right? And this sort of structure is called a probability tree. Okay, so with this I'll end my lecture on conditional probability. In the next video we'll see a simple example of how this is put into action, how the concept of total probability in fact is put into action. Alright, okay, so I'll see you later. Stay tuned. Thank you.